So let's get into it. So thank you so much for joining, everyone. Especially Gary, Karim, thank you so much for being here. Really appreciate you joining us today for our last week of the study group. This is the very last week. We have last two sessions this week, and this is the first one. We had Michael from Lighthouse speaking about the consensus layer data structure last week, and we follow up on the talk with the execution layer data structures today. And we have real experts here today, Gary and Karim from Besu, who've been working on the bonsai and their implementation of the Merkle Patricia tree. So I'm excited to learn from you guys the overview of the data structures and all kinds of different structures in the different kinds of clients. So yeah, thank you so much for being here, Gary. Or if you want to start, feel free to go ahead. Feel free to share your screen if you're ready.
Yeah, sure. So I put together a see. Oh, we gotta grant permission. I think that should work. Okay. Yeah, it looks
Yes,
like that is
perfect.
working.
Yes.
Um, yeah, so we're going to explore the Ethereum execution client state and kind of the different solutions and implementations that have evolved over time through the different clients. Um, as Mario said, I'm Gary. I work on Besu as a core dev, and Karim is joining us as well. He's really our deepest subject matter expert on state, so he's here to make sure I don't make too many errors. And with that, I think we can start. So the Ethereum state has remained largely unchanged since it was originally specified in the white paper in 2016. Um, but that's to say that the Patricia Merkle tree has remained largely unchanged. There's work afoot right now to move to Merkle trees or some other vector commitment strategy. But what we're going to talk about right now is the current mainnet Patricia Merkle tree implementation and how the different clients implement that. And despite the fact that the state implementation spec hasn't changed since 2016, the implementations in different clients definitely have evolved over time, and really different. Today, the execution clients really differentiate themselves by their state implementation. I'm viewing the presentation here that I'm sharing. So if there's any questions or chat, feel free to Mario just to interrupt me, or if we want to, feel free to interrupt along the way if there's something you want to ask. Um, but yeah, I can't see any questions, so just let me know. Great. Um, Yeah, so I think what we want to do is start with an overview of Patricia Merkle trees. Since they've been around in Ethereum since 2016, there's a lot of resources on the internet that talk about how the tree is structured, how the hash commitments work, and so forth. They're varying degrees of depth and quality. So I don't want to like belabor that point too much. But what I do want to do is just kind of give you at least a primer if you're not already aware of how the Patricia Merkle tree is specified and works. I want to give you an overview of how it works so you can understand the different implementations, why they are the way they are in these different clients. So just quickly, a Patricia tree is a prefix tree. And that means it's compressing the edges of the tree to try to minimize the depth of the tree as much as possible. You want to keep the tree as shallow as possible. You might have seen prefix trees like a good example is like how to store all the words of the dictionary in a single tree structure. It's kind of like one of those classic interview questions. You might be familiar with it in that regard. Um, Ethereum's Patricia Merkle tree also has the Merkle aspect, where Merkle trees are a type of hash tree that allows you to commit to the contents of the tree in a secure, verifiable, and succinct way. Um, and lastly, the Ethereum Patricia Merkle trees are hexary, which means they have a branching factor of 16. For each node of the tree, it can have as many as 16 child nodes below that in the tree. So when we put all that together, we have a hexary prefix hash tree. And I think a good way to intro to overview what the how the tree is structured is to look at the different data nodes themselves, the nodes that are involved within the tree. We can add the kind of cryptographic hash commitment stuff on via examples as we go through this. But since we're doing an overview, I think it's good to just kind of look at the three different types of nodes that you'll encounter in a Patricia Merkle tree. You'll have branch nodes. Those are the intermediate nodes within the tree. They don't store data directly. Instead, they are like the branching factor. This is the hexary portion of the Patricia Merkle tree. There are extension nodes. They compress, like in this diagram, these are the extension nodes. They compress some portion of the key space. Like if you have a deep section of the tree that doesn't have any branches until you get some significant depth into the tree, and then you get the path differentiated for these leaf nodes that are in there. What that's going to do is it will compress that path space so that you don't end up with an unnecessarily deep tree. That's kind of the Patricia portion of the Patricia Merkle tree. And then you have the leaf nodes. These are the things you actually are storing in the tree. This is the data that you really want to store in the tree. These other two node types are really just there to facilitate tree traversal and the proving of the state. Yeah, so again, the tree provides succinct verification of state, and it allows you to prove some subset of the state. That's really the Merkle portion of the Patricia Merkle tree. So looking at branch nodes to start. Branch nodes, as I said, those are those intermediate nodes that link the keys and paths, and they contain hash references of their child nodes. They're hexary. This is the hexary portion. They have as many as 16 child nodes. What the actual data that's stored in a branch node is an array of child node hashes. It's not like pointers to the nodes. It's actually the hash of the value of the child nodes. So when you look at this branch node in a logical fashion, you can think of it as like an array with 16 slots. So it's hexary. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. You can think about those addresses in the array as indexed by a hex digit. They actually kind of define the path through the tree. So as you're branching through the tree, you will go to like the A slot or the 0 slot and traverse through the tree in that manner. Okay, that said, back to extension nodes. These nodes, they, as I said, compress the access through the tree. They collapse some portion of the prefix that doesn't have any branches. They minimize the tree depth. They keep the tree as succinct as possible and as shallow as possible. And it reduces, effectively reduces the read and write amplification. So if you had to have a node that was, I don't know, say 16 layers deep, but you could express it as just an extension node to just a couple of leaf nodes, you can minimize dramatically the amount of read and write that you're doing to that tree. So these are all just specified in the Ethereum white paper for how the Patricia Merkle tree works. And then finally, the leaf node itself. This is the data element that we're actually storing in the tree. It's referenced by its branch node. The branch nodes reference its by its hash, the hash of its value. Like say this is an account leaf, you're going to hash the contents of the account, like its nonce balance, storage root, and code hash, and you would hash that data structure, and that's the reference that would be in the branch node. But when you locate this tree, or this node in the tree, you're actually locating it by its address. So if you think about that same leaf node account type, say its account was like 00 ABCDEF. When you go to insert that in the tree, you don't insert it with its actual address. You insert it with the hash of its address. This is for me, when I first looked at this, I was that was a little unintuitive. I didn't really understand why you wouldn't just store it by its address. And then I thought about it a bit more. And the reason that we do it this way is so that we can't attack via like a depth attack the tree. if you were to able to write, arbitrary entries into the tree, you could create an arbitrarily deep portion of tree. You can kind of attack grief Ethereum by allowing the tree to have unnecessarily deep nodes. Like at its worst, you could get, or not at its worst, but at its fullest, the state tree as it's defined currently could have a depth of 64. You might have a 64 deep node. And if somebody wanted to grief Ethereum, they could just, create two accounts that are one leaf off, or two storage slots that are just one portion of path away from each other. So you could force like this really deep uh, tree branch that you would always have to, an Ethereum node would have to traverse when you're interacting with it with transactions. So, in order to get away from that, in order to mitigate that attack, uh, it's specified in the white paper that we insert via the hash of the key. So we end up with a balanced tree, because the hash function is going to be, seemingly random. It's going to be well distributed and seemingly random when you hash the account path. So you end up with this, nice balanced tree, and it's difficult to attack because, like, you can't predict what if you're trying to craft a specific address or a specific slot that will attack the tree at a certain depth. It's certainly more difficult. You've got to use a lot of computational resources to do that. It's basically infeasible to attack the state in this way. So that is the reason why we index by hashed values in the tree. Okay, so that said, let's look at the anatomy of a tree hash key. Since elements are stored by the hash of their key, the tree keys are 32 byte hashes. So if we consider an example like the mock dead beef account, so dead beef, dead beef, dead beef, dead beef. When we hash that account address, it's going to hash to 3D, 7F, 32, B5, et cetera, et cetera, et cetera. So this is the key you would use to locate the account dead beef, dead beef, dead beef, dead beef in the tree. To store the node in the tree, to find the path through the tree where we actually insert these values, we break that hash key up into 4-bit nibbles. It's the Ethereum tree is hexary, so there's 16 values. Each branch can represent 16 children. So it's just convenient that 4 bits defines. It's not convenient, it's by design that 4 bits determine 16 different potential values. So what's convenient though is the hex view of that hash happens to present as nibbles. Like the first 4 bits of this address is 3, and the second nibble, the second 4 bits is D, and 7, and the fourth is F, etc. So when you go to insert in the tree, when you're trying to find an unused location in the tree to insert this value, you're going to traverse down the tree first at the D location, and if there's a branch node there or a conflict, you're going to go down to the next depth, and you're going to be looking for the D slot, see if that's unoccupied, the 7 slot, the F slot, etc. So that's really convenient. So you can look at any hash in hex and just intuitively know what its path through the tree is going to be. Okay, so to bring the Merkle portion of this in, to bring the hashing in, the cryptographic commitments, let's look at some examples. This is a really simple 2-leaf example. So we have an EOA1 and EOA2. And this is a toy example, so I just did this for fun because it's easy to type in and remember. But let's say that the hash of the EOA1, say the hash of its account is 00 ABCDEF coffee 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 coffee. And similarly, let's say leaf node 2, its value hashes to FF ABCDEF dead beef dead beef dead beef dead beef. So when we insert these into the tree, the root node is going to be a branch node, and the first nibble of this leaf address will be 0. So the hashed value of this leaf node will go into location 0 of this root node, and the first nibble of the second EOA is F, so that's going to go in the F location. So at the end of this tree, we have a root node with its 16, an array of 16 slots basically for hashed references. The 0 would be occupied and F would be occupied. And we take that array and we hash that array and we get the state root. So this state root ends up being 8A31 ED B66, etc. What's great about that is this is a really succinct commitment to the state of the tree. If there's no configuration of the tree that would also hash to this value. So if when you insert these values into the tree and you do all of the hashing at each level, you know that the state root represents exactly this state. So you, just this value here, you can use to commit to the entire state of the tree across all of the different nodes. Granted, this is a toy example because it's only a three node tree. So if we go a little bit deeper and we add a branch node, we can fiddle with these, toy hashes, address hashes here, and say instead now we're using 00 A B C D E F coffee 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 coffee, and in this one EOA2 is doing 0F A B C D E F dead beef dead beef dead beef. So when we insert these into the tree, nibble 0 is the same for leaf node 1 and 2. EOA 1 and 2 have the same first nibble. So this is not an unoccupied spot. We need to have a branch node here. So when we insert EOA 1 and 2 at the next depth, we check their next nibble. So this one is EOA 1's nibble is 0, and EOA 2's node second nibble is F. So there's no conflict there. We can now just directly take the hash of this leaf node, insert it into the 0 position of this branch node's array of child hashes. And same over here, we take the hash of this leaf node's, this account value, and put it into the F location of this branch node. So again, we have an array of 16 elements with 2 elements populated. We hash that value, we get 54, 509, etc. And we put that hash value into location 0, since this is the 0 nibble path still. We put that into location 0 of the root node. And when we hash this root node, we get the state root F5, 5C, etc. So again, this state root commits to this and only this configuration of state. It's a, again, super succinct way and secure way to verify consensus of state across different nodes. Okay, lastly, extension nodes. I don't know that we really need to think too hard about extension. Is that a question? Or yeah.
Maybe just the question about how the elements are stored in the array. For the unoccupied slots, are they just undefined or are the elements set to 0?
They are null elements, and like an implementation detail is that this is going to be an RLP encoding of this particular array. So there's null elements will have a specific encoding in RLP, and then what you're going to do is hash the RLP representation of that array. I didn't want to go too deep into that, but that's functionally that's how those elements will be represented and how they'll be hashed.
Thank you.
RLP is run length prefix encoding. If there's a lot of talk about the RLP on the net as well. It's just an encoding style, encoding algorithm. Okay, back to extension nodes. Again, I don't think we need to think too hard about extension nodes to really understand the differences in state implementations across different clients. But just to kind of close the loop, an extension node, if you recall, compresses some portion of key space. So if we fiddle again with our toy hashes here and say that the hash of this address is 00 ABCDEF 00 coffee coffee coffee, and this one's 00 ABCDEF dead beef dead beef dead beef, they have 8 nibbles of common prefix. When we go to insert this in the tree, we would have to go we would have a conflict at depth 0, a conflict at depth 2, 3, 4, 5, 6, 7, and 8. It would be the ninth nibble before we actually get to some portion of the path that's differentiating these two nodes. So if we didn't have an extension node, then we would have to have a tree that was like 9 or 10 nodes deep, depending on how you think about it. An extension node compresses that bit of common key space. It compresses all of 0, 0, A, B, C, D, E, F. So we don't need to create this unnecessarily deep tree structure. The extension node points to the branch node. Like the prior example, the branch node points to the two leaf nodes. We hash these two leaf node values, pop them into the array for the branch node, and then take the hash of the branch node and put that into the extension node. In this toy example, the extension node actually becomes the state root. It becomes the root node. It's a toy example. You wouldn't actually see that in practice, but it helps to fit the example on the slide. So just keep that in mind. Extension nodes are typically going to be found deeper in the tree. Okay, so that said, I think that gives us enough understanding of how the state is represented in the tree. It's going to be useful to look at a state. Oh, sorry. So I didn't talk about the leaf types themselves. So in the Ethereum Merkle Patricia tree, you're going to find two leaf types. There's going to be an account leaf, which would be in the account tree, and you'll find a storage slot, which would be a leaf in contract storage. The account leaf types are going to be either an externally owned account, like what you would typically use as a user to interact with Ethereum, at least historically, or a smart contract account. And regardless of whether it's an EOA or whether it's a smart contract, you're going to have the same data structure. You're going to have a balance in ETH. You're going to have the nonce. You're going to have a code hash, and you're going to have a storage root. So on an EOA, historically, code hash and storage root are not used. An EOA doesn't have code. An EOA doesn't have storage. So you end up with the empty hash for code and the empty tree hash for storage root. Just an interesting tangent in EIP 7702, EOA code hashes get repurposed. It's a special delegation mechanism that points to a smart contract that an EOA can delegate to. And go check out EIP 7702 if you want to know a little bit more about that, because that's just a change that's coming about, at least in how EOAs are encoding their account state. Okay, and the second type of leaf you're going to encounter is storage. Contracts need storage, contracts need code. The code hash I mentioned earlier, code hash is an attribute of the account itself, the account storage. So the code hash is kind of an implementation detail, but the code that's deployed will hash to a specific hash. It's going to be, deterministic. It's going to be distinct. There's no reason really not to just use the code hash as a key to look up the code in the key value store. It's an implementation detail. There's maybe reasons to implement it one way or another. But the simplest way to think about code is just a blob that gets stored in a database by its code hash. The storage, however, it is its own Merkle Patricia tree. Storage has contracts have storage that kind of present as a map of uint 256 to uint 256. So a 256-bit value key maps to a 256-bit value. But essentially, this is all like Merkle tree inception, in that each contract is going to have its own Merkle tree and its own root hash. And that root hash, when you change storage, this gets mutated, and it will get stored in this storage root for the smart contract account. Okay, now with that, we've kind of covered all of the bases at a high level about how you can represent state. But let's look at how you might mutate the state, because the state transition is maybe not a confounding, but a complicating factor about how you would represent state. So we have another toy example where we can have EOA for account A wants to send 2 ETH to EOA for account B. So in this state, we have EOA A is here. It's got a branch node X and the root node up here. Our tree depth is 3. We've got an EOA 2, which is B here, and its branch node is XN, and that propagates up to the root node. So let's say EOA 1 wants to send 2 ETH to EOA 2. What we're going to do in the EVM is we're going to decrement EOA 1's balance by 2 ETH, and we're going to increment 2 ETH to EOA 2. Since EOA 1 is kind of originating the transaction as well, its nonce is going to change. So the value of this account, its account state, is going to change. So its hash is going to change. Its path won't change. To get to this node, the path will not change, but the hash value of its account state will change. So therefore, we're going to update the hash value in its branch node, and then we'll send the hash. This obviously its value is going to change because its array of child hashes will change. And we'll hash that and push that up to the root node. Same with EOA 2. Only its balance changes, but still its hash will change. So propagate that change up to the XN branch node, propagate that change list of hash of the array of hashes up to the root node. So as I said, we are rehashing A, we're rehashing B. We push those hashes up into XN and X. And then subsequently, we will push the hashes of X and XN up into the root node, and we will rehash the root node to give us our new state root. And I think that gives us enough. If there's any questions, now is a great time because we're going to start talking about how Besu implements this and has implemented this since we started, since there has been some evolution there. So if you've got any questions you want to ask before we get into implementation details, now is a great time for that. I'm going to stop sharing, Mario, because this is the point at which we're going to use Karim's recording.
So before starting the video, so in this video we will talk about the difference between forest and bonsai and why we decided to move from forest to bonsai. So in this part I will mainly focus on the modification we are doing in bonsai that are related to the state. Bonsai, it's not only state modification, it's also a lot of optimization, it's a lot of improvement. But I will mainly focus on the state part because bonsai it's a really big subject. We added also a lot of feature around bonsai. So we have some blog. We are trying, as soon as we are some new features available or some new information, we are trying to publish some blog. So maybe after the meeting, I will see if we can share more blog like that. If you want to understand more bonsai, what we can do with bonsai, you will have all of the information you need. In Besu, we have two kinds of way to manage the state. We have the legacy implementation, this is forest, and we have a new implementation, bonsai, and bonsai is today used by default in Besu. So why we decided to implement a new way to manage the state is because we found that with forest, there are a lot of issues regarding performance, regarding the size of the database. So we tried to find a new solution in order to fix all of these issues. So forest is a hash-based Merkle tree implementation. So nodes are stored and accessible by their hash. It seems to be normal to do that because when you want to compute a state root, you need to use the hash of the different tree node, and also a parent will have the hash of the children. So yeah, it seems to be normal. And it's why also all of the clients before were using an implementation similar to Forest. But as the state was growing, as we had more and more transactions in the block, we found that the state management, so accessing the state and updating the state, was taking more and more time during a block processing. So I will try to show you what kind of issues we had with Forest. So for example, if I want to read an account in order to retrieve the balance or the nonce, so what I will have to do is to take my address, I will hash this address, and the hash of this address will give me the path to follow in the tree in order to retrieve the leaf that contains this account. So in my example, I will start by reading the state root node, and I will find that it is a branch. So if it's a branch, you can have 16 children. If you look at the path, so the first nibble is 0. So I will take the hash in the index 0. And this hash will give me the hash of the next tree node to read in the database. So at this moment, I had to read the database one time. So I will read the new tree node, and I will detect that it is a branch. So as before, this branch can have 16 children. I will take the hash, the next nibble, and it's 1. So I have to take the element at the position 1 in this branch. So at this moment, I had to read the database 2 times. I will read the next tree node, and yeah, it's a leaf node. We found the account just by reading 3 times the database. In a block, you don't have to read only one account. You have to read a lot of accounts, a lot of slots. And if you have every time to read 3 times or maybe more, it will impact a lot the performance. We have another issue with Forest, is how we are generating the keys. So in Forest, it is a hash. And hash is an access pattern that is completely random. So in the database, our keys are sorted. So if our access pattern is random, we cannot benefit from block-based caching system. So it's another problem regarding performance when we want to access the disk. In Forest, we have another issue when we want to update the state. I will give you an example with 2 accounts, account A and account B. So in this example, we'll have 7 entries in the database, so for the intermediate node and also for the account definition. I want to transfer to it from the account A to the account B. So what I will do is to modify the leaf that contains the account A, because the balance will be updated, and I will also update the leaf that contains the account B. As X depend on A and Xn depend on B, hash of X will also be updated. And it will be the same for Xn, and it will be the same for the root node, because the root node depend on X and Xn. So as we are saving by hash, this modification will create 5 new entries in the database. So it's only a transfer between 2 accounts, and the state is very small. But in the mainnet, the blocks are more complex. We have more state modification, and the state is bigger with more intermediate node. So each block will add a huge amount of new entries in the database. This is the kind of problem we can have with Forest. The size of the database that is growing too much and also very fast. And we have also the performance when you want to read the state because of the number of disk accesses and also because we are using hash for the key. So we decided to change how we are managing the state. Banzai, it's a location-based Merkle tree implementation. So nodes are stored and accessible by their location and not by their hash. And with Banzai, we have also a flat DB. So I will take the same example as before, but with Banzai. So to begin, I will want to read an account in order to have a balance. So as Forest, I will take the address and I will compute the hash of this address. But instead of climbing the tree, I will directly ask the flat database. Flat database is a key value database where the keys are the hash of the address and the hash of the slot key. You can have directly the balance of the account or your slot value. The second example is when you want to update the state. So as we are saving by location, so the key in the tree database will be 0x for the root node, 0x00 for the first children of the root node, etc. And we'll have also the flat database with as a key the hash of the address and as the values the account definition. So we'll have 7 entries in the tree database and 2 entries in the flat database. If the account A wants to send to it to the account B, this modification will update the leaf and the leaf will have a new hash. as the leaf will have a new hash, the parent will also have a new hash. So we will still create this cascade of modification, but as we are not saving by hash, we are saving by location, it will not create new entries. Because even if the hash is different, the location is still the same. So instead of adding new keys, we will replace the old keys by the new one. So in this case, we will update the 2 entries on the flat database, and we will also update 5 entries in the tree database. No new entries will be added. We are just adding new entries when the structure of the tree is modified. So when we are adding, for example, a new account, or when we are adding a new branch or something. But how we can retrieve an old version of the state? With Forest, it's not really complex because we keep all of the tree node and all of their version. So we can always retrieve the state of a previous block. Everything is in the database. But with Bonsai, as I said before, we are replacing the tree node every time. So we don't maintain the history. We only have the current state, so the head. In Bonsai, in order to fix that, we implemented a trilog mechanism. So what is a trilog mechanism? In order to explain that, I will use the example of Git. So when you develop something and you have different commits in Git, every commit is not a full copy of the code. Instead of duplicating the code for each commit, what you are doing is to create a diff between the 2 commits. So the diff is what kind of line you removed, what kind of line you added. And thanks to this diff, you can regenerate the code as it was for the commit you want. So we are doing something similar with Bonsai. We are generating every time a new trilog, and the new trilog will be a diff between 2 blocks. So it's a flat representation in the trilog. We are just adding in this trilog all of the leaf that we are modifying. So the account we are updating, the previous value and the new value, the slot that we are modifying, the old value and the new value, and code. And like that, we have the modification we are doing between 2 blocks. And if I want to go back to an old version of the state, I just have to apply this diff. And like that, I will have the balance of my account in an old block or something like that. I don't have to keep in the trilog all of the intermediate node because when I will modify the leaf, I will be able to regenerate all of the intermediate node. So it's not needed to keep everything in the trilog, just a flat representation. So you can see an example of what kind of information you can have in the trilog. So as I said before, account modification. So you will have account A, account B with the previous value and the next value, slot modification, code modification, etc. So for example, when I want to transfer some heat from A to B, I will generate a trilog like that. So we will have account A with the previous value. We can say, for example, the balance before was 100. And after the transfer, the balance was 98. And the nonce was increased by 1, for example. For the account B, we can say maybe the balance was 0 before, and after receiving the transfer, the balance was 2. If I want to roll back to an old state, I just have to take the trilog and revert all of the modifications that I find in this trilog. So for example, I know that the account balance is 98, so I will go back to 100. For account B, it's 2, I just have to go back to 0. So I will modify the leaf and all of the intermediate node will be recreated. And like that, I can retrieve the state as it was before in a specific block. I have 2 kinds of way to manage the state. We have the legacy implementation.
Yeah, it's all for the video.
Cool. That was definitely a whirlwind, like definition of and differentiation for forest and bonsai strategies. So it's really the difference between using a hash key for storing your trinodes and using a path-based key. So does anybody have any questions or want some clarifications about like hash versus path-based trees?
Yeah, I was just curious since you still need the Merkle Patricia tree for creating the state root hash for consensus. How do you consolidate your bonsai tree with the MP tree, Merkle Patricia tree?
We consolidate it with bonsai. We consolidate it by implicitly pruning, like because we only keep one version of the tree on disk at any time. It's we just keep this single. That's why it's called bonsai, because we keep this single manicured tree, and the trilogs will allow you to mutate that single tree forward or backward. So if you need to see historical views of state, you can mutate in the case of bonsai, it can mutate it in memory to have some historical perspective of what state was. But functionally, the tree and the hashing remain the same. What's really different is how we address those nodes in the database, because we're using the path to the node as the key. And then when we're storing in the database, rather than the hash of the node as the key in the database. So that's really the big differentiator in terms of like auto pruning between a hash-based and a path-based tree.
Yeah, instead of using the hash we are finding in the branch in order to get the next key, we will know directly what is the location of the next node because we have the path directly thanks to the hash of the address. So yeah, it's just how we are climbing the tree, but the content of the tree node in the database, the RLP of each node will not be modified, it will still be the same, and we are computing the stage root, it's also the same, so yeah.
Gotcha. And these tree logs are also useful for handling like reorgs, things like that.
Yeah, yeah,
definitely.
yeah. It's also something we are using for the reorg.
Yeah, there's some neat features. Tree logs are almost like a block witness because they have pre-image and post-image values. It's kind of like a it's not a cryptographically, it's not a commitment, but it's kind of like a succinct witness to what occurred on a block.
It's similar to what we will have with stateless, but as Gary said, we don't have any proof with this trial, so the trial should stay in the instance of Bezo, so it will not go outside of Bezo, but it's completely similar to what we'll have with stateless, so the prior value and the new value. Just for stateless, we'll have proof like that we'll be able to share this diff to another client.
Gotcha. Yeah, I know you guys mentioned like that you do have the flat DB for the key value pairs, and I know that other clients like Aragon will use flat DBs. I'm just curious on you know, how would you say like pros and cons of having just like a pure flat DB versus you guys' kind of like hybrid approach?
You know, the next section of this is going to talk about how different clients implement their own different strategies, and we're not experts on other client code bases, but I think we have a pretty reasonable understanding of their schema, so we can probably address that here in just a minute if you hang on just a moment.
Word. Sounds good.
Yeah, just to confirm, I'm also not getting comments in the chat. So if people are trying to comment, please do so in the Discord or raise your hand.
I'm going to go ahead and okay. I'm not sure where I left off in the presentation that I was screen sharing, so I might have to jump through, or it might just work. Let's see. No, it's in the right spot. So what Shane was alluding to, variations on state schemas in different clients. And I'm going to say it again, we're not experts on other client implementations. What I think of this as, this portion of the presentation is like a starting point for you to go start exploring other client implementations. Like if you want to have just a high level understanding of what these clients offer, what their benefits or trade-offs are, or fundamentally how their schema is working. So that said, other execution clients have kind of a grab bag of different strategies. Some have the hash-based tree still. Some have a path-based tree. Some have both hash and path. Some implementations flatten the tree. There's some interesting development in that regard, so that it's not hex array, at least on disk. And then there's like a history tracking strategy that is beneficial for archive nodes. I think we should start with Geth. And the reason I think we should start with Geth is because Geth has evolved kind of separately from Besu, but we've both sort of arrived in a very similar place with regard to our path-based implementation. Geth, when it started, like most clients, all clients probably, originally had a hash-based state tree implementation, just like Forest in Besu, had all the same problems that Besu had with Forest. In 2020, Geth implemented snapshots. Snapshots are effectively a flat database of all of the different block change. This is a single state tree that's kept on disk, similar to Besu's Bonsai. However, it's a hash tree still, and the changes accumulated in memory for up to 128 blocks. And every time the head of the chain goes beyond 128 blocks, they would collapse, they would compress. How do you call that? They commit that 129th block diff to disk. So they keep this running 128 block behind state implementation, state tree on disk, just a single hash tree. But because it's a hash tree, pruning is still a challenge because you have to track all of these hash nodes that may or may not be updated. They might be part of some prior reader. They might be part of some prior state that's still necessary, and it's difficult to track those changes. So if you recall, like older versions of Geth, you might have to shut it down so that you could do offline pruning, so you could regain that storage. But that's a problem that Geth fixed in 2023 by introducing a path-based state scheme. Like Bonsai, it's a path-based single tree on disk, so it's implicitly pruned. I think it's probably best to characterize Geth's implementation and how it differs from Besu, because they have like this, my understanding, like I said, we're not experts, but my understanding is that Geth maintains a snapshot, a single tree that's like a fixed distance behind head, whereas Besu typically has a more fluid relationship with what state is stored on disk, and we typically will commit the most recent finalized block as the state root that's on disk. So that's kind of an operational difference, but I mean, they're very, very similar. They took a different route to get where they are, but they're both very similar in their state implementation for path. And Nethermind has some very interesting solutions. They have the production code right now is half path. And they have a kind of new, more aggressive rethink of state, which is Paprika. Half path is kind of an evolution of the hash-based model. It's still a hash-based tree, and there's multiple, like a forest of hash trees that exist on disk. But the keys are prefixed with a portion of the path. When they save the nodes of their tree, they have some partitioning that ends up, let's look at my next slide. I don't want to front run my next slide. Yeah, so there's a section byte, there's 8 bytes, up to 8 bytes of the path prefix that's going to go into the tree key. And there's the length of the path. Like this is, like I said, this is up to 8 bytes. The path length is going to specify how much of that 8 byte path is relevant in the prefix there. And then the 32 byte hash that normally would be the hash key for a hash-based tree. And similar, let's go ahead and maybe skip to the next slide. No, I should probably say the benefits here. Like the benefits, because like Besu, Nethermind currently is using RocksDB, and RocksDB is a log structured merge tree implementation of a database, which means that everything is stored as sorted strings. The files that make up a RocksDB database are sorted string tables. So you'll have these sections of the key space that end up getting lumped together, partitioned together into these individual sorted string tables. It gets more complicated than that with the log structured, merge tree stuff, but fundamentally, all of the files on database are sorted. So when you sort by the path, say you've got this section byte and this path prefix, you're going to have all of the elements, or most of the elements that are relevant to descending down a path, stored next to each other on disk. So you get improved data locality. So when you are reading off disk, when you're reading from cache, it's going to be more performant. Cache is going to be more effective. Compression is going to work better because they're stored together. When you keep data close together, the individual compression is going to work a lot better. So even though they're storing more data in their keys, they're adding 10 bytes to the tree keys here and 10 bytes to the storage tree key here. This actually ends up a net reduction in the size on disk because of the way the RocksDB is able to compress that sorted data. So just a quick bit about the section. It's a byte, but there's only 3 different values, as I believe. Again, not an expert, but if it's like a hot section of the tree, like near the top of the tree where you're going to constantly be getting changed hashes, changed values, and so forth, that path length would be less than 5. So that would be like what 10 or fewer nibbles worth of path would be stored in, it's partitioned off in section 0. So you can, so that's going to be like the hot part of the tree. 1 would be the less hot part of the tree, and it's going to be storing more of the path prefix. The path prefix would be up to 16 nibbles because it's 8 bytes of path prefix, and all of those are going to be stored together on disk. So you can kind of see how this access pattern is going to make it where the hot portion has its own usage profile, and the deeper portion will have its own usage profile, and the section byte value of 2 means that it's account storage, storage, contract storage. So that is partitioned off differently. It just kind of creates a good usage profile for sectioning, partitioning this stuff by where it exists in the tree. And again, this is the path prefix stuff. It's 8 bytes, up to 8 bytes. There's the path length. And then finally, there's the actual 32-bit byte, 32 byte hash value that is the key for the tree. So it's kind of a clever way of incorporating path to gain the advantage of path locality and the advantage of attribution, really, because this also helps, I understand, with pruning, because since Nethermind's half path is still using a hash-based tree, all of these keys have deduplication issues. Like you don't know which one needs to be removed when you're moving state, like when you're expiring or pruning a tree. It's pretty challenging to do that with a hash-based tree. So my understanding is that this prefix makes that pruning somewhat easier. So I think half path is like a kind of a gateway to a Nethermind's path-based solution, which is Paprika. And I am just kind of coming to terms of what all Paprika is and does. So it's in development. It's not production code. So this is just what's coming in a preview, and it's coming from a person who doesn't understand it all that well. So take all this with a grain of salt. But my understanding is that Paprika, at its core, implements its own page database. So like it's not using RocksDB, it's not using MDBX, it's using its own invented here PageDB. And I think it is Ethereum aware. It's like Ethereum is a first class citizen in PageDB. And I think the PageDB dependency is going to be something that you could actually incorporate to other clients, I believe. So if someone were interested in writing a client, they might be able to use PageDB and have an Ethereum aware, first class citizen Ethereum database. One of the interesting features of Paprika is that it is collapsing the tree. Instead of having this branching factor of 16, Paprika changes the tree structure to have a branching factor of, by default, 256. So each of the pages represent 2 nibbles of path instead of 1 nibble of path in a 16 hexarray tree. Each nibble each page represents 2 nibbles. I got a squeaky dog behind me. Sorry, I don't know if you hear that. So what this ends up doing is it reduces the read and write amplification because the tree is a lot more shallow. I was talking with one of the developers, and I think they said in the last time that they were testing this on mainnet, they were able to represent the full state tree at a depth of I think no deeper than 5, and they were able to represent contract storage storages at a level no deeper than 7. So it sounds pretty promising. As I said, I don't know a whole lot about it yet, so I don't want to go too far into the weeds on it. I do know it's designed to be path-based and commitment agnostic, so that it can be used. This is kind of their gateway into Verkle. I don't think that they're going to be using the half path in Verkle. They're going to be using Paprika for Verkle. So that's kind of their forward-looking strategy, and it seems really interesting. Karim and I were talking about maybe borrowing the idea of flattening the tree to 256 airy flattened tree. Paprika pages, the way the PageDB is set up, there's a root page, there are data pages, there's abandoned pages, and prefix pages. Data page is kind of like some segment, some natural segment of the tree, some segment of the path in the tree. And an abandoned page, as I understand it, is a data page that is it's basically a data page it's no longer current. It's not the head state, so it's available to be pruned or reused by the database. And the prefix page, I believe, is analogous to extension nodes in a hexarray tree. But yeah, keep an eye on that. It seems like it's pretty interesting. Like I said, forward compatible with Verkle. There is capacity in the design for archive. I don't think that it's implemented, but I think that there's design capacity for having an archive node using Paprika. And check out the design docs. They've got a good design doc on Paprika at the Nethermind GitHub repo. Go to Nethermind ETH Paprika under docs design. It's a pretty good primer on that. Okay, so Aragon state implementation. I know not a ton about the Aragon state implementation, but I have a high level understanding of how they're segmenting their schema. What's interesting is that the Aragon state representation is used by both Aragon and Reth. And Reth has kind of borrowed that. It has a shared history with the Acula project from the Aragon team. So I suspect that's probably why Reth has at least similar to the Aragon v2 state implementation. Aragon state storage, it's known for being a very tight archive format and very quick access to historical information for like RPC, supporting block explorers and so forth. It's very good at that particular use case. What's interesting is it maintains both the plain state, like it's got flat DBs, as Shane alluded to. Aragon has 2 flat DBs, as I understand it. They've got the plain state, which is unhashed keys, like instead of hashing the account key and hashing the slot keys so you can insert it into the tree, their flat DB, one of their flat DBs is uses the unhashed, the pre-image as a key in that state. And it's also got a hashed state where the keys are hashed. My understanding of the hashed state is that it exists largely to support calculating the state root. What's interesting about the plain state is that it means that Aragon and Reth are uniquely positioned to be able to provide pre-images for the entire Ethereum state, which is a problem for all of the other clients like Geth and Besu and Nethermind don't maintain pre-images by default. There's features that you can add pre-images, but it's not the default. You can't expect any of those nodes to have unhashed keys for their state. So when you want to migrate to Verkle or to Starkle or to whatever the next state iteration is going to be, somebody's going to have to provide that pre-image store to Geth and to Besu and to Nethermind, and in all likelihood that's going to come from an Aragon state implementation, whether that's coming from a Reth node or from an Aragon node. It's very convenient and handy that they happen to have that for Ethereum. The Aragon also, it's V3 specifically. Aragon V3 is new, so I don't want to talk too much about it because it's hot off the presses, as I understand it. But they have this notion of frozen state data that can be imported quickly. It's the Aragon, an Aragon specific format, so it kind of plays into their sync strategy. Their the BitTorrent based incremental frozen state sync strategy, and makes for a really fast sync in Aragon 3. It's largely because of the format that they keep for their history. Logically, the Aragon state schema is, as I said, the head state is made up of 4 tables, as I understand it. The plain state, that's the flat DB in plain unhashed keys. The hashed state, which is the same thing but with hashed keys. And there's a tree of accounts and a tree of storage, and those two are there. They're basically the intermediate nodes, the extension nodes and the branch nodes and the state root that are used to calculate the state root. I believe Aragon only keeps a single hashed tree, single version of the hash tree in the tree for the tree of accounts and tree of storage. That's subject to verification, but I believe that's the case. Where Aragon's like archive use case is served well as these tables down here: the account change set, storage change set, account history, and storage history. The storage change set and accounts change set, anything that's the change set is keyed by the block itself. So like whatever happened at, for example, block 4, you're going to have some storage that was changed in block 4, and there's some account that was changed in block 4. This table is indexed by the block number and the account, the key that was changed, either the account key or the storage key. So when you want to do a historical query, say what was the state of block 4, you're going to go to the account change set and see what happened in that state. If you actually want to see if you want to see what happened in that block, you would use these tables. If you want to see what the state of an account was at block 4, you would go to the history tables. The account history and the storage history, they're keyed by their account and their account storage slot. So if you want to see what the dead beef account looked like at block 4, you're going to go to the account history and say, give me the pre-image for this block at its closest time it was changed. Say we want to know what it looked like at block 12, and it was changed in block 4. You can go to this account history table and say, give me the most recent version of this account based on block. I'm looking at the state at block 12. What's the state of this account? And it's stored as a oh boy, we're running over time a little bit. Or are we okay? Yeah, so accounts history is good for looking at accounts and storage at a specific point in time, whereas these guys are more about seeing the change set for a particular block. And with that kind of is the end of my understanding of the different execution client implementations. It'll be interesting to see what the Nimbus execution client is going to be doing. But yeah, that's one of the few that I don't know anything about yet. And with that, we can, if we have time, we can talk about the archive solutions. All of these path-based systems have challenges with archive since they're implicitly pruned. So Karim has a bit that's talking about where we're headed with path-based archive.
So in this video, yes, I will try to explain how we are trying to implement a Bonsai archive-friendly feature. So it doesn't seem to be normal to have Bonsai and archive in the same sentence, because Bonsai is more for near-head state, but we found different ideas in order to implement that. So I cannot confirm that in the future the Bonsai archive implementation will be as I'm describing today, but yes, this is the main idea we have, and the feature is still in development, so it's not yet in production, but we hope to have maybe something this year if it's possible. If it will be really nice if we can have something this year. Yeah.
so much, Gary. And yeah, I have the video already. Before we started, we are good on time. I just wanted to check if there are any questions meanwhile. I mean, it was a lot of information, a lot of different approaches from all the different clients. So, folks, if you have any thoughts, any questions, maybe about some specific approach. Otherwise, I will get started. Yeah, I will switch my mic and please let me know if you can hear it again.
Recently, we decided to check if we can use Bonsai as an archive mode. Because we added a lot of optimization, we also reduced the size of the database with Bonsai. So yeah, we tried to see if we can have a solution to use Bonsai also for all state and not only for near head. What is an archive mode? An archive mode will help you to retrieve the history of an account, the history of a slot value.
Yeah.
So
Same.
we need to be able to retrieve very old state in order to do that.
Okay,
So
can
in
you
order to help regarding this part, we
give me a second. Okay, now the debugging will be fun.
We could probably talk through it if you want. I don't think that I think there's only a handful of slides. If you, Kareem, do you want to just try and talk through it?
It's only a few minutes.
I can try, yeah.
Okay. Do you have the slides? Do you want me to keep sharing it, or?
Gary, do you want to share the slide?
Sure. Yeah, I'll share the slides.
Yeah.
Yeah.
Okay. Thank you, guys. Sorry about that.
So as I said, could you hear me? Yeah. Yeah. So as I said, we are trying to implement a Bonsai archive-friendly feature. Today, in order to provide archive feature, we are using Forest. So we still have to deprecate Forest. So in order to fix to keep everything, we'll have the same database size as Forest, and it will just be useless to work on that. So in order to fix the issue regarding the flat database, what we decided to do is instead of having only the last version in the flat database, we will modify the key in order to have as the prefix the hash of the address with a suffix, and this suffix will be the block number where we modify the account. For example, in this case, we have an account A, and we can say in the block 1, the account A was created. In the next block, the block 10, the account A was modified. And in the block 15, the account A was modified again. So in the flat database, we will have 3 different keys. And each keys will have as prefix, as I said, the hash of the address, and as a suffix, the block number where we had the modification. So we'll still have a lot of duplication, but the flat database is still smaller because we don't have all of the intermediate nodes. So it will still be better than a Forest node. But how we will be able to retrieve the good version regarding, for example, if I want to retrieve an account A, what was the balance of the account A in the block 11? And seek for priv will help you to retrieve the key that is the closest to a specific key. And if it's not equal, it will be just the key before. So for example, if I want to retrieve the balance of an account as it was in the block 11, so I will ask RoxyB to give me the key where the prefix is the hash of the address of the account A plus with the suffix 11. As the key is not existing in the RoxyB database, what we will have is the key with the suffix 10. But as we are not modified the account in the block 11, having the version of the account A in block 10 is valid. So the result we will have will be okay, and we'll be able like that to retrieve the version we want. But having only account balance or account nonce or slot value is not enough. Normally, we should also be able to prove that the data we are finding are valid. And if you go to the next slide, in order to validate that the data we are retrieving is valid, we can use something that we are calling Merkle proof. So Merkle proof will help you to be sure that an account B is included in the Merkle tree of a specific state. For example, if I want to be sure that the balance of the account A was 10 in the block 10 in the block 10, I will have to have a proof that this balance has really this value in the state of the block 10 thanks to the Merkle proof. But as we said, Banzai is only keeping the head of the state. So if we want to be able to regenerate an old state, we have to do a rollback. But if we really want, for example, in the mainnet today, if we really want to have the state of the Genesis block, it will be too many rollback and you will not be able to do that. It will consume a lot of memory and the node will not be able to recreate this state, too much data. So we had to find a new way to avoid all of this rollback in order to retrieve the state. So if you can go to the next one. So in order to fix that, we decided to create some checkpoints. So instead of saving all of the state of each block, we will create a checkpoint of the state after n block. So for example, in this case, I will create a checkpoint of the state of the block 2. I will not save the state of the block 3. I will not save the state of the block 4. But when we reach the state of the block 5, I will create another checkpoint. And like that, instead of doing a huge amount of rollback, I will just have to take the checkpoint that is the closest to the block I want, and I will have to do rollback or roll forward in order to retrieve the state I want. So if you go to the next slide, for example, so the distance between each checkpoint will depend on your need. For example, if you want a longer interval between checkpoints, the size of the state, the size of your database will be smaller. So it will be better if you don't have, if you don't want to have an important database size. But the performance will be lower because as your checkpoint distance will be bigger, you will have to do more rollback or roll forward in order to recreate your state. But if your priority is the performance, you will have to decide to use a shorter interval. And like that, you will have maybe a database that is bigger, but you will have less rollback and roll forward in order to recreate your state. So the performance will be better. So it will depend on the need, and it's something we want to add as a flag, so the user will be able to decide the size of the range he wants. So next slide.
Yeah, I think it's interesting to mention that there aren't any path-based databases that give you historical proof of the Merkle trees. Is like even Aragon's archive-friendly format doesn't have those prior versions of trees, so they can't provide historical get proof unless you have a large full archive node, like a full archive node Geth or a full archive node Besu or a full archive node, like a hash-based tree implementation. of some of these other clients.
So I heard that Guess is working on something similar. I'm not sure how the Guess implementation will work. I've just heard that they are trying also in a path-based archive feature, but I'm not sure if it's already in production or if it's still something they are trying to implement. But yeah, clearly, as Gary said, I don't think a lot of clients can provide this kind of feature with a small database size. So just to explain how we are able to retrieve a state from a checkpoint. So as I said, if you want to prove an account that was in the state of the block 4, what you will have to do is to just find the checkpoint that is closest to 4. So for in this case, it will be 5. And you just have to do one rollback in order to recreate the state of 4. And like that, you will be able to generate your proof. So if you have only one trial, one rollback to do, the performance will not be bad. It will be something similar to the to when you want to generate a proof from a near-head state or something like that. So the performance will be really good. And as I said, if the size of your database is not something important, you can just have a smaller range, and the performance will be not a problem for you. But it's still in development, so we still have a lot of modification to do in the code. We also have to do a lot of benchmark to be sure that everything will work correctly. But we already have some PR that are ready, and yeah, the next step will be to finish the test and trying to merge that in the main branch.
I think we'll probably deliver the Bonsai archive feature incrementally, where we have the FlatDB based. It solves almost all of the RPC use cases except for get proof. We'll probably be rolling that out ahead of the checkpoint feature that gives you proof at any arbitrary block in history. So yeah, it's probably going to be delivered incrementally. Yeah, hopefully this year for the full set.
It's also something we want to be optional. So maybe some people don't want to generate a proof. They just want to have the historical data of account and slot. So it will be useless for them to create all of these checkpoints and increase the size of the database. So for this user, only having the flat database feature will be enough. So with that, they will have a Bonsai archive with a really, really small database size. And people who want to be able to generate a proof will have to activate this feature, and it will take more space, but yeah, it will still be something smaller than Forest.
With that concludes what we have to present, and we're pretty close to time. So if anybody has any questions, now is a great time to ask them. I think we're going to probably share the slide deck with Mario. So if you want to refer to this or any of the references in it, will be available after.
Well, thank you so much, guys. Amazing. Yeah, awesome. Yeah, right at the time. Great timing there. We still have a couple of minutes for questions. So if there are any thoughts, questions, folks, please go ahead. It's one of the last opportunities to chat with core devs in our study group. So please don't be shy. Don't be hesitant. Okay, we have a question from Tiro.
Yes, sorry, might be a bit dumb, but it's really hard to think about rollbacks and creating proofs for like a previous block being added to the chain. Like, is it useful to think of what would be applied to the new checkpoint as the inverse of the state transition function?
Exactly. Yeah, like when a rollback is essentially inverting that state transition precisely.
And so how would that work? You'd take this block and like in the example, the checkpoint of the fifth block, and do what with it, perhaps?
Well, we would, at least in Besu, we would take the trilog. Say if we're trying to get to block 4, we would start with the checkpoint version of block 5, and we would take the trilog for block 5, and we would unapply it. We would revert all of those changes in memory so that we could now have a view of all of the Merkle tree at block 4.
So, for example, if you added an account from the block 4 to the block 5, if you want to roll back, you will just have to remove this account. If you incremented the balance of an account in order to go to the block 5 by 2, in order to roll back, you will just have to decrement this account by 2. And it's like that. You can recreate the state as it was before, because all of the leaf will be recreated, and as all of the leaf will be recreated, all of the intermediate node will be recreated as before also, and you will have the state of the block 4, and like that you can generate a proof.
Thanks. Thank you very much.
And as Gary said, we are also creating a lot of copies. So I didn't really wanted to talk about that because it's really complex and it's not really linked to the state. But with Bonsai, we are trying also to implement something that is thread safe. So for example, if you want to generate a proof thanks to an RPC API, you will create a copy of the state and you will roll back this copy. Like that, you are not impacting the main state that is used in order to follow the chain. And every time you will call an RPC API, you will have a new copy. So for example, if you have to respond to two RPC API at the same time, just an example, each RPC request will have its own copy. And like that, we can have really something that is thread safe.
Yeah, so I think you guys mentioned statelessness a little bit, and I know one of the key blockers for that is the size of Merkle Patricia tree proofs, and we have Verkle as a proposition to reduce this overhead pretty significantly. Just curious, from the perspective of you client maintainers, what are some of the more main engineering challenges in going from Merkle Patricia tree to Verkle? You guys even started experimenting with that yet, or is it just too early stage?
So in Besu, we are already working on Verkle, so we have a first implementation. We can follow the current DevNet, and we are also working in the transition from Patricia Merkle tree to Verkle. But when we implemented Bonsai, so at the beginning it was Dano Ferry. So when Dano implemented Bonsai, he was also thinking about Verkle. So it's also why, for example, the trilog is similar to the witness we have today in Verkle. We have prior value and next value. So it was not really hard to modify Bonsai in order to implement Verkle. So today we have a Verkle implementation and Bonsai implementation, but the two implementations are sharing a lot of stuff. And like that, we can just have the specificities that are in the Verkle package for Verkle, and also for Bonsai, they are in a specific package. So it's in the Besu side, I want to say that it was not really hard to implement Verkle. And I think we have really also a clean architecture that help Besu to be compatible with different kind of tree and with different kind of storage format. Also, for example, when we decided to move to forest to Bonsai, the code was modified in order to be able to manage two kinds of storage format. So adding another one is not really complex because we already did the stuff, the kind of refactor in order to be modular. So yeah, in my opinion, I'm working a lot in Verkle. I didn't saw a lot of complexities. For example, in Verkle, we are also implementing a flat database. It's something that is really useless for Verkle, useful, sorry, for Verkle. And also something that is interesting is AsGuess is doing a lot of things that are similar to Besu.
when guest is implementing is writing a specification, it's matching in general very well with Bonsai. So, and with Bezu in general. So yeah.
I think
Nice.
some of the interesting challenges with Verkle is the cryptographic load that's going to be involved with generating those commitments, the vector commitments. So that, and then there's like scheduling and resourcing problems that revolve around, are we going to try to do binary trees with Starks? Are we going to try to do Verkle as it's currently implemented? And are we trying to be quantum resistant? Some of the challenges are really more about planning and resourcing than they are the actual implementation details.
And also Verkle is adding, as you said, some cryptographic stuff that are not really performant if we are comparing with Sketchak. But also, thanks to Bonsai, we added some optimization that will help for Verkle. For example, we implemented Bonsai parallelization. So Bonsai parallelization could help to do some stuff in parallel as pre-computing, doing some disk accesses in parallel in order to have something faster. We can also maybe do in parallel some computation, or maybe you can cache some recompile call. And all of this stuff can help also regarding the challenge that we have with Verkle. And yeah, we added also some preload in Bonsai in order to do in parallel as much as disk accesses in background. And it's also something that can help for Verkle. So it's really interesting that we are sharing the same base of code between Bonsai and Verkle, like that. Today, when we are working on some optimization in Bonsai, we know that will also help for Verkle.
Cool.
Thank you.
Thanks.